In this video, I'm going to demonstrate how we can use the Python scripts from the tool PRoTECT in order to run simulations of any of the four dynamical systems. I'm going to demonstrate using the discrete time stochastic system functions, which you can see here in both the serial case on the right hand side and in the parallel case on the left hand side. You can see the parameters which are required and optional for these functions listed here, where if you see an equal sign, this means there's a default value, so this is optional, and the option would be that you're automatically choosing the type inside the equals. And these other terms are all required. If these are not entered, then the code will not work. Simple as that. Below you can see a list which describes how each of these parameters should be formatted. These formats in both the parallel and the serial case are almost identical. Even the b degree is the same. The only difference between them is that the b degree in the serial case will only run a single run of the barrier using that exact degree, while in the case of the b degree for parallelism, this is considered to be the maximum b degree. And so inside this function, it will calculate all of the even barrier values up to and including the b degree. If you pass in an odd b degree, that's not going to work. And so what we will do is we will remove the odd value and consider all of the even b degrees up to that value. So in terms of the other parameters then, we have dim. This is the dimension of the state space or of the dynamics that we're considering. We have this parameter avoid regions, which actually no longer exists, so let me delete that one. We have the initial region, so this will be L is for lower bound and U is for upper bound. So this is a NumPy array which is separated by commas for each of the dimensions. We have the unsafe region, which is a NumPy array of NumPy arrays. And the reason we do this is because we can have multiple unsafe regions. And so for each unsafe region, we have a NumPy array with commas separating the lower bounds dimensions from each other. And then the same for the U unsafe would be the upper bound separation. And we collect all of those NumPy arrays together in a larger NumPy array. And this is how we pass in all the avoid regions. I'll make this clear when I show you one of the example codes a bit later. We also have the state space, the lower bounds and the upper bounds L space. Again, this is a NumPy array using commas to separate each of the dimensions lower bounds and then each of the dimension upper bounds. We have X. This is a list of SymPy variables. So whatever this list is that you pass in, it should match up with your function dynamics. So if you choose a two-dimensional system with the variables x1 and x2, then the function dynamics should also include x1 and x2. We also have a list of SymPy variables for the noise. These are var sigma, and again, when we pass in the noise parameters, if we use var sigma 1 and var sigma 2, then we should be having them inside of the dynamics function as well. T is the time horizon. This is a required parameter and it's used inside the calculation of the confidence value. Now we get onto some of the more optional parameters. So by default, the noise type will be of type normal. We do make a check for the type Gaussian because these are the same thing. But inside the GUI, you will have noticed that we only have normal. So this can be normal, it can be Gaussian. It's the same thing. We also offer noise types of exponential and of uniform. And if you are to choose one of these noise types, then of course you will have to provide the equivalent parameters for that noise type. So for the normal distribution, we expect a standard deviation, sigma, to be provided as a NumPy array with commas separating each of the standard deviations of each of the dimensions, and the mean as well, which by default will be assumed to be 0 in the GUI setting, but here you'll need to list them out. For the exponential noise, we assume that you will provide a rate parameter, again a NumPy array where the rate parameters for each dimension are separated by a comma. And then for the uniform distribution, we expect a lower bound and an upper bound list for each of those dimensions. A is the lower bound and B is the upper bound. It's possible to use our code in the stochastic setting to optimize, and so if you wish to do this, then you should set this value to be true. By default, it will be set to false. If you do set it to be true, then you will need to provide a lambda value, a value for lambda, which is just a constant, can be a float type value, and this will need to be provided. Otherwise, if you do not choose optimize to be true, then all three of these values, gamma, lambda, which are both the level sets, and the constant c, these are float values, and it's optional whether you set them or not. If you do set them, then the code will try and find a barrier using those particular values. The confidence is a float value that should be between 0 and 1, and this is the minimal confidence that you are expecting the barrier certificate to have when we verify. So it might be that it's not possible to get the confidence that you require, in which case they'll say that there's no feasible solution, but it may be that we can find a barrier with, say, 0.8 confidence or 0.7 confidence or whatever it is that you are looking for. The last optional parameter is L degree. This is the Lagrangian degree. And if you wish to change the degree of the Lagrangian multipliers, you can do that using this parameter. By default, it will just be set to be the same as the dimension. Now, let me show you one of the examples of how you can use this, how you can use these functions and write your own code in order to set up the example. So here I have a 3D example of a room temperature system, and you can see it's discrete time and a stochastic system. What we're doing is we're importing some values that are, some libraries that are important. So we're importing time so that we can calculate how long our simulation takes. We're importing SymPy, and we just rename this as SP just because it's a bit shorter. We're importing NumPy, and so NumPy creates the arrays, and SymPy is what creates these SymPy variables. We also are going to import some functions from our tool. So we're importing that parallel function that I mentioned, and also the single value. If you only want to run one run of these, you don't need to import both, but I just wanted to demonstrate that both of these happen inside the code. And this location is assuming that you've added the main directory of PRoTECT into your Python path. So the next thing we'll do is we need to set up this if name is main. This is very important for the way that the code will do the parallelism. If you don't have this, then it's very likely to cause an error. We set a value for the dimensions. In this case, we set 3. And now we describe the initial region. So it's a 3-dimensional system where all 3 dimensions have a lower bound of 17, and all 3 dimensions have an upper bound of 18 for the initial region. We only have one unsafe region, and it is between the values 29 and 30 in every dimension. And so because we need to do a NumPy array of NumPy arrays, then I have this second function which just collects these together and puts them into another NumPy array. If I was to have a second unsafe region, I could describe it using the same command here, maybe with 2 instead of 1, and then I would just simply list the next one as unsafe 2, for example. And this is how you can collect all of those unsafe regions together. Also describe the state space. The lower bounds are 17, the upper bounds are 30, and this is the entire region we're considering. The next thing we want to do is we want to create these symbolic variables that we're going to use for our dynamics. So x and var sigma are both required, if you remember from the function definition. And so this little function here, this will create values x1, x2, x3, etc. up until the number of the dimension. So in this case I have dimension 3, so I'm going to use x1, x2, and x3. In the same way for var sigma, I have the same function, and so I'm going to create var sigma 1, var sigma 2, var sigma 3. Now I'm describing the noise, so I'm going to assume that the noise type is of type normal, and I'm going to select my standard deviation sigma and my mean. And so here I've chosen 0.01 in each of the dimensions for my standard deviation, and the mean I've selected to be 0. My function dynamics are going to be described here. In this setting, because I have several variables which are repeated across the 3 functions, I can define them before, and then I'm going to use these as I describe the function here. So x with the square bracket 0 means my first value of this list here of my SymPy variables. So this is going to be x1, but I'm just using the list number of the way Python works is that 0 will be the first item in the list, and so that will be equivalent to this symbolic variable x1. And so for each of my dimensions, f1, f2, f3 are the different dynamics. So then I'll collect all of these together in f. I'll have my 3 different dynamic expressions, and I collect them into an array. Then lastly, I will set my time horizon. In this case, I've set it to be 3. Now the nice thing with Python is that you can pass in a whole load of variables in one go into the function using a dictionary. And so this is what I'm doing. So I am using the key of the dictionary, which should match up with the function names of the variables. So for dim, I then am going to pass in the variable dim that I've set here. So this is passing in 3. And I'm doing this for each of these parameters, and some of them I'm not using, and so I'm just setting them to be none, or even you could just omit them and the default value would be selected. So in this case, because the noise type is normal, that is going to be here. And then we also set sigma and mean, but we don't need to set the other noise type parameters because we're not using them. In the same way, I'm optimizing, I've set it to false, and so I don't need to set lambda to any value. Now I'm selecting my maximum degree value, so this is the value b degree, and I'm initializing the time to calculate how long this will take, and then I'm simply using a variable called result, which will collect the output of the function, and I'm passing it in the first parameter, which is b degree, and I'm setting it to be 6. And then using this notation here, I'm passing it in this dictionary of all the other variables. And so this way, if I decide that I want to run it in parallel with just variables 2 and 4, then I can set it to 4, or if I set 6, it will be 2, 4, and 6. Finally, I'll collect the end time, and I've got a little print statement which will calculate how long it took in order to run this parallel simulation. All of these times are reported in the PRoTECT paper, which you can find on Archive or on Google Scholar. Yeah, if for whatever reason there's no barrier that can be found for any of those, there'll be some error commands which get printed out, and we will just return this print statement saying the result is empty. It should be quite easy based on these examples that you can find. I'll show you in the folder. So we have 3 folders inside of the examples. So this is my PRoTECT main directory, and I have benchmark stochastic, and these are all the stochastic examples where CTSS implies continuous time stochastic systems and DTSS is discrete time stochastic systems. And then I also have the deterministic ones where in the PRoTECT version you can see the discrete time deterministic systems and the continuous time deterministic systems. I've also provided the fossil codes which will be used for comparison with fossil. You can find these in the paper, and if you wanted to do some repeatability or comparison, you're welcome to use them. I'll just very quickly show you the continuous time difference. So let's take this nonlinear system, and so you can see in almost exactly the same way we still have dim, we have these, but here we have different functions, CTSS and parallel CTSS, which are all in the same functions folder. When I'm selecting the noise, I have slightly different noise terms. So delta is my NumPy array of Brownian motion diffusion terms. And then for the Poisson processes, I have the reset terms, which again are a NumPy array with commas separating the different dimension values. And for Poisson processes, we also have this Poisson rate for each dimension, which we calculate. When you're calculating barriers for any of the versions which are not discrete time stochastic systems, you don't actually need var sigma. That's only necessary for the discrete time stochastic case. And so we can just create the symbolic variables x here. Once again, we create the dynamics. And then you can see I have a slightly different dictionary where the noise terms now are delta rho and p rate, and I don't have the noise terms of the other system. And for the deterministic settings, you'll notice that these dictionaries are even smaller because there's even less parameters. For example, we don't need to do any optimization in the deterministic systems because the optimization will always be 100% as long as you can find a barrier. And yeah, once again, we have the parallel function here. So if you wanted to run it without parallelization, you can just omit this first term and just run CTSS, and that would just run it with the B degree value of 6 in this case. I hope that's been very helpful, and I look forward to seeing you in the next video.